In this lecture, we will be learning about the Rayleigh-Ritz method, which is a method used for finding out the approximate solution using potential energy, the total potential energy. So from spring elements, now we move on to bar elements. A bar element is nothing but a one-dimensional element which to which only axial forces are it is subjected to only axial forces. So it will displace in one direction itself. Okay, so the derivation of this method is given to you all, and I am going to solve a problem. So this is our first problem. Using the Rayleigh-Ritz method, determine the expression for displacement in a fixed end. So that means both the ends are fixed and it is subjected to an axial force P at the center of the bar. So at the center of the bar we have a force P. Okay, let the length be L. So we know this is L by 2 and L by 2. So let's begin. Let U be the axial displacement at any point, x. Okay, so this is our x direction. So U is the displacement at any point. Let U suffix P be the displacement at the load point. That means at the point where force P is applied, the displacement will be UP. Now the strain energy is given by half into integral volume. We know it is given by sigma, that is the stress, into the strain. Now sigma x means nothing but the stress in the x direction, or the axial stress. And epsilon x is the corresponding strain. Okay, actually it is not going to be with respect to dx. Since we are saying integral over volume, this will be dv. If we want the relation between strain with respect to the displacement, it is dou u by dou x, and the stress is given by Young's modulus times the strain. So Young's modulus and epsilon is this, so E into dou u by dou x. The area of cross section, okay, area of cross section of the bar, nothing is given to us, so we are going to assume that it is uniform over the length L, assumed to be uniform over the entire length L. So what we mean is, now we have a bar element here. Here we are looking at the front view. Okay, if I take a section here like this, I will see a square like this, and here is the point of application of this force. So it is coming out from the screen, okay, perpendicular to the screen right towards me. So let us assume that the area of this cross section is A. Okay, and the elemental volume is given, dV is given as the cross sectional area A multiplied by the distance dx. That means any short distance. Okay, so we are talking about only a small portion, so we are taking dx. Otherwise, the if you are talking about the entire bar element, it would be A into L. So we are talking about a small part only now. Substituting this, we get in the strain energy, we get half. Now dV we are replacing by A into dx, so the integration also has to be in terms of dx. Okay, that is in terms of x. Here we have at the start point x equals to 0 and at the end point we have x equals to L. That tells us about the length of the bar element. So integral will go from 0 to L. Let us substitute. For sigma is E into dou u by dou x into epsilon is again dou u by dou x, and dV is now given by A into dx. So removing the constant terms out of the integral sign, EA divided by 2, 0 to L, what remains inside is dou u by dou x the whole square dx. Now we have calculated the strain energy term. The next term we have to calculate is the work potential, and the work potential WP is given by the external force acting P into the displacement at that point of application of the force, which we had assumed to be UP. Okay, negative sign. So the total potential energy is now given by pi equals to strain energy plus work potential, which is EA upon 2, 0 to L, dou u by dou x the whole square dx minus P into UP. Let me label this as equation 1. Now, based on the Rayleigh-Ritz method, I am writing a short form, Rayleigh-Ritz method. Let us assume a displacement axial displacement at any point as, so this is what we saw in the derivation. It has to be of the form, now we are talking about one dimensional, so there will be no y and z, so the polynomial has to be in terms of only x. So let it be in terms u of x equals to a0 plus a1x plus a2x square. So in this equation we have a0, a1, a2 are Rayleigh-Ritz constants which are to be determined. Now we have already assumed a function. Next step is to apply the boundary conditions. At x equals to 0, that is at the left hand side, we know that the displacement has to be 0. It's fixed and there is no movement allowed, so no displacement allowed, so that since it is fixed. Okay, so substituting x and u in equation 2, we get 0 equals to a0 plus a1 into 0 plus a2 into 0 square, which means that our first constant a0 turned out to be 0, right? Now this is the first boundary condition. The second boundary condition is at x equals to L, that is at the right hand side. Again it is fixed, so there is no displacement allowed, u equals to 0. Substituting, we get in equation 2, we get 0 equals to a0 plus a1L plus a2L square. Now we already found out that a0 is 0. Okay, so here we get a1L equals to minus a2L square, or a1 equals to minus a2 into L. Let us substitute a0 and a1 in equation 2. We get u of x equals to a0 is 0 plus a1 is now minus a2L into x plus a2 remains as it is. So we get minus a2Lx plus a2x square. Another boundary condition that we could put is at x equals to L by 2, that is at half the span. We know that the displacement is up. Now let us call this equation 3. Substituting this in equation 3, we get up equals to minus a2L, x is now L by 2, plus a2 L by 2 the whole square. So we get plus a2 L square upon 4. This gives us minus a2 L square upon 4. Differentiating equation 3 with respect to x, we get dou u by dou x equals to minus a2L plus 2a2x. So if we remove a2 common out, we get 2x minus L in the bracket. Okay, so now why we have done all this is, in the original in the first equation, if we see in the pi equation, we needed two terms. One is dou u by dou x and the other one was up. So now we have got both. Let us substitute in that equation and let us rewrite the equation now. So we have pi equals to EA upon 2, 0 to L. Dou u by dou x is a2 into 2x minus L the whole square dx, plus actually it is minus p into up, but up is minus a2 L square by 4.